Imagine if you could extend your arm to twice its length. No, wait. Make that 100 times its length. Now imagine that it could lift 3 or maybe 800 times more than it can lift now. That'd be something. Actually, that would be a crane. One of the most useful machines ever created.
You see cranes in every facet of today's society, particularly when we're building. They're used for marine work. We see cranes on barges. We see cranes on the shore to load and unload the cargoes off of ships. We see cranes on railroad yards to unload the cargo there. We see cranes on practically every construction job.
It's like playing a big Donkey Kong game, trying to control that hook and steady the hook.
It's like everything else. As long as it keeps looking simple, we're fine. The complexity involved in a crane is unbelievable.
Cranes in a shop like this, you have to have them. I cannot envision even trying to do business or do things with the number of people we have here without them.
Cranes are hoisting machines that are capable of lifting loads vertically and horizontally as well. Some cranes even pivot around in what's called a slewing motion. And they come in all shapes, sizes, and types. From little forklifts to giant derricks. In between, you'll find gantry cranes, bridge cranes, even mobile cranes. The biggest crane of all? The tower crane.
This is a Painter SK 575 crane manufactured in West Germany. All the features that you see that are on the crane right now are state-of-the-art. The maximum load for this crane is 29,000 pounds, and all of this comes together in one point, 15 by 15 at the base of the crane and about 12 feet deep.
Tower cranes are often planted into the ground in a cement foundation that can weigh as much as 400,000 pounds and provides a solid anchorage for the structure.
When you do need a tower crane, it's because you need it 100% of the time. It goes in, it's one of the very first foundations that you put in.
J.A. Jones Construction is putting up a building on a challenging Santa Monica, California job site. To the north is a freeway. To the south, a police station. East and west are crowded streets. With a reach of more than 260 feet, this crane extends over the busy roads as it lifts material on its metal hook. But this crane's high-tech electronics will shut it down if it tries to lift something beyond its load capacity, or if the load begins to sway too much. Further, it can absorb tremors from earthquakes, a real danger here. Wind speeds over 30 miles an hour will shut it down, but it can withstand hurricane-force gales by going into weather vane mode, allowing the jib to release and swing in the wind. And given its proximity to the Pacific Ocean, this 150-ton, 110-foot-tall crane is built to resist salt and wind.
As you can see, we have a captain's chair, and I have two joysticks. Right-hand joysticks run the hoist up and down. Left-hand joysticks here runs a trolley in, a trolley out.
Tower cranes are simply big cantilevers. A cantilever is a structure that extends from a single support. The vertical mast of a tower crane anchors the horizontal boom, also known as a jib arm. At the end of the jib, a pulley is used for hoisting. Often the pulley can slide along the jib on a trolley as the jib pivots on the mast. The jib pivots because of a slewing unit, which incorporates the jib, a machinery arm, lots of motors and electrical gear, plus the cab where the operator works. Finally, counterweights at the opposite end of the jib act as an opposing force to the jib's load. It's that simple. Only, it's not that simple at all. In fact, the controls are quite complex.
It's all computerized. There's levers, there's switches. The crane operator has to be trained to operate those things. It's a matter of understanding the computer program.
This is our computer right now, our screen digital readout that can read me the weight chart, the radius of the trolley, how far out the distance I'm at. It reads the capacity of the crane, the wind speed factor, and the percentage of my weight capacity.
The computer and circuitry on this crane is almost as large as the cab.
This is our main computer panel right here, the A panel. Reads out the trolley, the swing motors, and our main computer, the brain of the crane itself. As you can see, pretty high-tech stuff.
Plus, it speaks German and French, in addition to English. Despite their size and complexity, cranes like this tower crane can be assembled and disassembled quickly. When the job's done, they're trucked to another site to be built anew. With the help of a portable crane on the back of a truck or tractor, the tower crane is constructed out of interconnected bars of steel, much like an erector set. Finally, the slewing unit is hoisted onto the mast. The whole process may take only a couple of days.
The crane has open web members. Another name for it is lattice. And that's really the structural guts of the crane that derives its strength. So you don't need to box it in and you don't need to cover it. As long as you have your structural skeleton to make it work, that's all you really need.
Tower cranes are assembled in sections when they help build very tall skyscrapers. They employ a hydraulic jacking device to hoist the jib, cab, and climbing unit up from the top of the mast, so that a new section of the crane mast can then be inserted underneath them. Theoretically, a crane could keep building indefinitely, although strength and leverage decrease as height increases. And when you're teetering on a 250-foot pile of steel toothpicks, leverage is important.
Actually, if you have motion sickness and you're afraid of heights, you wouldn't belong in the seat.
Cranes are hoisting maniacs. They literally pull an office building or a skyscraper up from its foundation as girders and partitions are lifted and positioned with the greatest of ease.
Well, this one loads everything into the building, moves all the formwork, brings up all of the reinforcing steel for the concrete, takes the forms from one floor to the other, brings in all of the other supplies for all the other subcontractors.
This crane and all the others like it do something else. They lift the economy.
It's hard to quantify the impact of cranes on our economy. The construction industry represents about 10% of America's gross national product. And you cannot build without cranes, so it's a very vital part.
Cranes have been helping our civilization move forward ever since we've had a civilization. Up next, ancient cranes. How early engineers may have used cranes to build the pyramids, the Colosseum, and the great cathedrals. Contractors can expect to pay as much as $20,000 per month in rental fees for a tower crane. Cranes will return on Modern Marvels. In Manitowoc, Wisconsin, they make cranes. Big cranes that travel. At over 640 feet high, their largest models rival some stationary tower cranes in their ability to lift heavy objects high off the ground. But with portability, they're in many ways more valuable. They even perform some of the same tasks. For that matter, they even assemble tower cranes. And they're designed and built right here.
Engineers pretty much are the designers of our cranes. There are several people, it can be anywhere from customers to salespeople that come up with the ideas, but really it's in-house engineering that comes up with the designs.
Manitowoc makes different types of portable cranes, from telescopic crawler cranes that can extend their jibs hydraulically, to boom trucks, small cranes that can travel the roadways and which sport modest telescopic booms. After the designs are approved, the next stage is manufacture.
Really, it's somewhat quite simple. It starts on the far end of the facility. It comes in as raw steel. We cut, we burn. On the plasma burn table, we have large weldments, small weldments that we make. All comes together in the assembly area. Once it's assembled, it comes out here to the test yard, and from there we knock it down, put it on trucks, and ship it to the customer.
The advantages of a mobile crane are obvious. They can go from job to job with a minimum of site preparation. With their jibs and mast all folded up, they can transport themselves. And by deploying outriggers from their chassis to create a larger base, they can achieve suitable stability. And all you have to do to pull up the outriggers is press a button. How beautiful is that? Maybe beautiful is the wrong word.
Cranes aren't designed aesthetically. They're a working tool. You think of them like a mule. They're there to do work. They're not an architectural feature of anything because they're temporary. They're not going to stay there. So the only time you're going to see them is during the transitional period of construction.
True, they're a little awkward looking, but for something still in its awkward stage, the crane has been around for an awfully long time. In fact, no one really knows when they were first used. But they were almost certainly employed when man began using large stones for construction, roughly 4,500 years ago. For example, to move the 5,000-pound stones that make up the pyramids of Giza. Early cranes used pulleys. A pulley is a wheel, sometimes grooved, that employs a rope to convey energy. When a pulley is connected by an axle to a frame or block, which in turn is connected by a rope to other pulleys, it creates a block and tackle. Now you have mechanical advantage. Mechanical advantage results when a fixed amount of force, for example, the force exerted by a single man, is increased many times through the application of simple mechanisms like the pulley. It all depends on a simple-looking physics formula. Work equals force times distance. In this case, rope is used to move a 200-pound object 2 feet. Employing a pulley, the effort exerted by the man is only 100 pounds. But the distance pulled is 4 feet of rope. The more pulleys, the greater the mechanical advantage.
Cranes had a very slow evolution. It's hard for us to trace it because there was really no documents of it, and of course there was no pictures other than maybe some paintings, and cranes weren't a favorite topic of painters.
Sometimes the best evidence of an ancient crane is the end result of its effort. Certainly the Hanging Gardens of Babylon and the Colossus of Rhodes could not have been built without some sort of crane. But clues like this image of a crane being used to construct the Colosseum in Rome, found on the tombstone of one of the contractors, explicitly show that cranes were employed by the ancients. Wooden cranes were used during the Middle Ages to help build Europe's massive cathedrals. Treadmills were used as engines, generating the energy to power the cranes.
It's interesting that they use human beings inside of like a big barrel, and that turned the wheel which wound the rope and lifted the load.
During the later Middle Ages, early tower cranes like this one were being designed by Leonardo da Vinci. This particular example may even be the first mobile crane ever built. By the mid-17th century, wooden cranes were a familiar sight at construction projects, such as this one in Paris, building the Royal Bridge. But during the 19th century, a new building material would revolutionize the role of the crane.
With the advent of mass-produced steel in the late 1800s, that just opened the door for cranes because we found a new building material, and with that we were able to increase our structures a great deal. We took a quantum leap.
Steel allowed engineers to reach new heights, both artistic and altitudinal. Steel structures like the Eiffel Tower, the Statue of Liberty, and the hundreds of turn-of-the-century skyscrapers were dependent on new modern cranes, which were also made of steel and thus exceptionally strong for their weight. Although early cranes were steam-powered, ultimately they would employ the internal combustion engine. Companies familiar with structural steel construction and companies experienced with heavy-duty equipment began offering cranes for large-scale projects. As architects continue to make bigger structures, crane manufacturers joined them in the race for the sky. Since the skeleton-framed cranes could easily be built up by simply adding more sections. Today, companies can make cranes to whatever height their clients need. Some have topped 35 stories. Nearly every iconic architectural and public works project from the Empire State Building to the Hoover Dam, has relied on cranes. Cranes are easily the most important piece of large equipment on any job, and they can be one of the most complex.
For example, you may have a 300-ton capacity mobile crane, but that doesn't mean that it will lift 300 tons anywhere it will reach. And so you have stability limitations, and that would mean that the crane would be lifting the maximum capacity with the boom fairly vertical. As you begin to boom down or to extend the reach, what we call the radius, then you're not able to lift near as much.
A crane operator needs to know not just what his maximum weight limit is, but where and what that maximum is at any given point in the arc of his lift. If he doesn't, he could seriously injure himself and his co-workers.
You're defying the law of gravity and you're doing it in close proximity to people. So anytime that you do those things, then there are a number of bases that have to be covered for the lift to go safely. And many times those bases aren't covered, and you have some pretty serious accidents, and many times they're very catastrophic.
Nearly every serious crane accident ultimately can be traced back to human error. Often, the end result is a crippled crane. Occasionally, lives are lost. One of the most serious modern crane accidents was in San Francisco in 1989. 5 people were killed when a crane fell 16 stories. Next, some of the largest cranes ever built never lift anything heavier than a svelte 30-ton container. A crane operator can make between $60,000 and $100,000 per year, depending on seniority and location. Overtime can push the number even higher. Cranes will return on Modern Marvels. Looming like steel dinosaurs along the waterfront of major port cities, giant container cranes are the workhorses of the crane world. These 200-foot-long, 350-foot-high, 22-story cranes stand at the pier waiting for their ship to come in. But they don't wait for long, and they don't stand still, because these mega cranes can roller skate.
A container crane will move up and down the dock. That's the gantry motion. It will move in and out towards the ship and away from the ship. That's trolley motion. And it'll hoist up and down. That's hoist motion. So we call them a gantry crane because they gantry.
Rolling on wheels along rails parallel to the docks, gantry container cranes weighing 1,320 tons have revolutionized the shipping industry with their efficiency. Each ship is divided into 50-foot sections, with a few cranes loading or unloading at the same time, each crane working a section while discharging 30 containers an hour.
To offload a ship today, we can do it probably in 8 hours with a container crane, whereas it used to take maybe 3 weeks before.
As our ships get bigger and bigger, our cranes have to get bigger and bigger to lift these container loads off the ships and also to load them. And so the cranes that we were using 12, 15 years ago are obsolete. We can't use it.
In the year 2000, the Port of Oakland, California received the first 4 of 8 brand new container cranes, made to order and shipped fully constructed on a special ship from Shanghai, China. Price tag? About $7 million apiece. The trick was getting them to fit under the Golden Gate and the even lower Bay Bridge.
Obviously, as the cranes get higher, you want the height of the crane to be higher to control the boom lift. And so we designed those cranes to be within a meter of the bridge when at low tide. So we had to be really careful when we brought them in. The ship is designed to ballast up and down during the offloading to maintain the height of the ship during tidal changes, so we could actually ballast the ship right down to the water level when it came under the bridge.
Because they're unloaded, fully assembled, the cranes like these at Oakland are usually up, tested, and working within 15 days of arrival. Which is good because ports like Oakland are always busy. with an average of 5 to 7 massive ships loading and unloading each day. Electrical engineer Wan Yong, who works for ZPMC, the company that built the cranes, helps ensure that the cranes are working properly. Wan Yong gives the cranes a quick test drive before they go operational. He helped design and install the systems that coordinate the 20 computers on this crane. Each crane has its own 12,000-volt substation housed in a room way up inside. The computers each track a different function, such as air conditioning or the elevator. But the main computer operates the hoist, trolley, and gantry moves. Unlike on a tower crane, the cab on a container crane does some traveling. 2 joysticks operate the hoist and the trolley. Another computer keeps the cranes from gantrying into each other.
An interesting thing about a container crane is that it's a very specific design. All it does is move containers. Handles cargo on and off of ships. They don't do heavy loads, they don't do a lot of unusual things, but they do move containers very fast.
The cranes are designed around standard container sizes, usually 40 feet by 8 feet. Inside each container are 20 to 30 tons of goods to be shipped or unloaded, possibly onto a truck or a rail car. A coupling device in the crane hoist connects with the 4 corners of the container, hooks it, then hoists and swings it up and away, as high as 140 feet above the dock. Using containers to ship things may seem obvious, but they've only become the industry standard since their first application in the 1960s. Early dockside cranes didn't need to be nearly as strong or tall.
Every box sat on a pallet. We reached down with a crane, lifted up the pallet, took it off, set it on the dock, and then moved the pallet around with a forklift. The first containers were built here, and the first container cranes were made here. We designed the crane and the containers and the ships to handle the containers all at the same time. They were designed together.
Now the whole process works like some sort of blue-collar ballet as the containers lift and swing and drop off the trucks and onto the ships.
You don't realize it because they make it look pretty simple, but if you get up there and try and operate it yourself, you'll see that a 40-ton container hanging from a set of wires that's 100 feet long is a big pendulum. And you have to be able to control that. That's not easy to do.
Not all waterfront cranes are giant container cranes maneuvering to load big ships. Some, like this railway gantry, are more construction-oriented. And these seasoned veterans actually help build ships, towboats, and barges in Jeffersonville, Indiana, along the Ohio River.
Well, the shipyard was established in 1830s as the Howard Shipyard, and later became Jeff Boat in the late 30s. And at that time, the cranes were put in place by the Navy. The originals now have been replaced by the ones we have now, which are 1960, 1970 models.
Weighing in at about 300 tons and topping out at 95 feet, these gantry cranes are put to all-purpose use here in this shipyard, moving unwieldy materials and building ships. Sometimes they have to work as a team.
We use a 2-crane lift anytime that we get anything that's heavier than 55 tons. And we do that with our side boxes, our bows, and anything that's above 55 tons. These are very complicated. The cranes, you must keep the load level. The cranes must work in unison so that you're not putting strain on one and not the other, and you must keep the load balanced.
These cranes aren't the only cranes working the waterfront. Jeff Boat has access to a floating crane mounted on a barge. Good for those hard-to-reach places just offshore.
The barge crane we have here is a Clyde. It was built in 1949. We mounted it on a barge probably in the 70s. It has a capacity of 30 tons. We use it basically for taking out engines, replacing engines, gearboxes, and towboats.
Next, they can climb up skyscrapers. They can skate next to ships. Is there any place a crane can't go? Port of Oakland, California, the fourth busiest port in the nation, has over 31 gantry cranes working more than 19 miles of waterfront. Cranes will return on Modern Marvels. There's one. There's another one. That right there, it's a crane too. Cranes have so ingratiated themselves into our world that once you know where to look, you can't help seeing them.
When you think about it, everything that's made has to be lifted and moved at one time or the other, and cranes play a big part in doing that.
For instance, driving down the road, that long arm sticking off the back of that tow truck, it's a crane. Sort of a miniature version of the mobile construction crane. Yet these hydraulically powered derricks are capable of picking up any vehicle certified to travel the roadways, including big rigs weighing over 70 tons. Using portable remote controls, these trucks can lift while the operator stands a safe distance away. Like their mobile crane cousins, tow vehicles use outriggers to brace against the ground. And they have booms with complete 360-degree mobility. The crane is such a vital element of the auto towing industry that it was a key component of the very first tow truck ever built. A twin boom crane mounted on the back of an old Cadillac. Even before the tow truck made its first appearance, railroads solved the problem of derailments with a similar steam-powered crane that ran independently along the rails.
When you had a car that came off the tracks, generally the railroad would bring in their derrick. We call it the big hook. And they would use that to lift the cars back up onto the tracks. Our derrick was built in 1917. It was modified in the 1970s to diesel-electric power. And it has 150-ton lifting capacity.
These specialized railroad cranes also move the occasional fallen tree and rolled boulder. Take the hook off the railroad derrick and replace it with a big scoop. Then switch out the wheels for tires. And you've got yourself a construction shovel. Remove the tracks off the shovel, stick the crane on a barge, and you've got a drag line or dredge. These giant machines help scoop out canal bottoms and maintain ports. And their floating platforms enable them to reach places only a vessel can go.
Another application is what we call a clamshell, which most kids are familiar with it because when they play arcade games, one of the arcade games is you have this crane with a big clamshell on it to go and pick up a toy. So a clamshell is, I would classify as a crane also.
For sheer variety, no place beats a warehouse for crane spotting. Here at Washington Iron Works in Gardena, California, workers use gantry cranes and forklifts to move large pieces of architectural metal around the shop. Yep, even a forklift is a crane, because it can lift up and move over. But look closer. The very walls and ceiling of this shop have cranes.
We have the overhead bridges here, which are 5-ton rated service bridges, one old truss-style bridge, two more modern family single-span girder bridges. We have 2 3-ton overhead trolleys in the architectural shop. We have another 5-ton rated bridge just next to here on the stockyard. I don't even know the count on how many cranes we have here, but there's a lot of them.
These bridge cranes are steel beams which run on rails built into the side of the warehouse walls and which run the length of the warehouse. A trolley runs along the beam itself, and a pulley on the trolley can raise or lower a hook. Workers at the warehouse can manipulate each function of the crane using hand controls. Without them, working this iron would be nearly impossible.
It's not a luxury, it's a necessity. Just think of it this way. 3 or 4 people would have to pick up a 250-pound piece. One man with a crane can pick that up and move that safely and get it to where it has to be. And you multiply the savings on 3 or 4 guys spending 15 minutes moving a piece as opposed to one man doing 7 minutes. The savings are phenomenal.
Workers who operate the cranes go through a rigorous training session and weekly update seminars. The cranes are also built with warning signals to prevent them from crashing into each other. Plus, they slow down within 10 feet of each other. Or at least they're supposed to.
There have been accidents before where that mechanism has failed. It's never affected the integrity of the crane or the load or ever hurt anybody. We just had two cranes smashing together.
Cranes are so abundant that even movies and television shows make use of special lightweight ones. That's because in Hollywood, cranes and cameras go together like sex and violence. It's lights, camera, cranes, here on the set of TV's Charmed.
The crane allows us to place the camera up in the air, make swooping moves onto the boat, go above the water, be 2 or 3 feet below the dock to see right on the surface of the water. Just in general to put the camera in areas where we can make moves that a dolly can't make.
The Charmed crew is using a lightweight jib made by Aerocrane that won't put too much stress on this rickety dock. Hollywood has been using cranes to get those big sweeping shots for years. In the early days, it didn't matter if you used a squeaky old construction crane. But after the introduction of sound, directors like Cecil B. DeMille and Alfred Hitchcock needed quiet, agile, yet sturdy cranes to get that million-dollar shot. Called cherry pickers, they were modified from cranes developed during World War II to place bombs in airplanes. Many of today's movie cranes are often lightweight, portable, and easily assembled.
The Aerocrane, as opposed to being a welded box, welds tend to crack under stress and pressure, is extruded aluminum. You get basically the same strength out of a much smaller profile without welds. And a smaller profile makes it easier for the crew to carry it around. The Aerocrane can be built by one person.
Today's cranes don't have to be sturdy enough to hold a camera plus a director and a cinematographer. With omnidirectional remote capabilities and video monitors included, all you need to do is stick the camera on the end and make the magic happen.
Cranes give the directors much more versatility in filmmaking. As opposed to just a couple of talking heads, the director can take the audience from being intimate in a conversation between two people, pan back, give the audience a view of what they're looking at, also change their perspective. They're no longer at the table, they're a fly on the wall.
Next, cranes go from being a fly on the wall to a bird in the tree, as one group of scientists plant a tower crane in the middle of the woods. Plus, another group of scientists have launched cranes into space. At this very moment, one is clinging to the International Space Station. The largest single-bucket digging machine ever made was over 222 feet tall and could hold 220 cubic yards of material. This crane, called Big Muskie, was scrapped in 1999 after 22 years of service. Cranes will return on Modern Marvels. Cranes continue to find plenty of use here on Earth, and clearly not just at the familiar construction site or deep water port. Some are even working amidst the temperate forest greenery of ancient conifer trees here in the Pacific Northwest.
It's mostly Douglas fir and western hemlock. Those are the most dominant trees in this particular stand. It's kind of a prerequisite to not be afraid of heights.
If you care about global warming and trying to have some influence on that process, then you obviously care about how places like forests influence that.
Here at the Wind River Research Facility at the Gifford-Pinchot National Forest in southwestern Washington state, scientists use a tower crane to study the canopy of this ancient old-growth forest. Some of these trees are over 500 years old.
The crane is extraordinary because it allows you to take very heavy equipment up through the canopy. You can work anywhere within that three-dimensional space of the crane, which is about 6 acres, that isn't occupied by something solid. And it allows you to take very heavy equipment, various kinds of sensors and gases and things like that, into these tree canopies, which you would not be able to do otherwise.
Erected in 1995, the Wind River Canopy Crane tops out at 250 feet are 25 stories high. The only canopy crane in North America, it is also the tallest canopy crane among the half dozen in the world. It lifts researchers as high as 220 feet, allowing them to conduct experiments in the trees, winter, summer, rain, or shine.
What we're doing today is we're getting an indirect measurement of transpiration, that is loss of water vapor from the needles of these conifer trees, with a device called a porometer.
They are also determining the amount of water tension on columns of water within each tree as it pulls moisture up like a straw from its roots and out through pores on those topmost needles. These scientists are toppling long-held beliefs about old-growth forests. For instance, these ancient Douglas firs and hemlocks are absorbing more carbon dioxide than a young forest does.
This forest literally breathes, and when the sun comes up in the morning, there's an initial burp of CO2 that's been moving up through the stand all night long. Then, of course, all day long, it's taking up the CO2 as photosynthesis kicks in.
One of the great advantages of canopy cranes, at least for tree physiologists like us, is that they allow us to study trees as whole organisms and to try to understand how they coordinate and integrate their activities, because previously all we could do would be to access a small portion of the tree.
The U.S. Forest Service Northwest Research Station, in conjunction with Gifford-Pinchot National Forest and the University of Washington, coordinates as many as 30 research projects at any given time here at the crane. But the man who deftly places these scientists in the canopy is Mark Creighton.
This crane uses 3 basic controls, 3 functions, and those would be slewing motion, as in a swing, trolley, which allows our basket to go in and out, and then we also have a hoist, which allows the basket to go up and down. And what we have here is a 3D readout, which is unique to tower cranes for the most part. It'll give me a position, the distance that my basket is out, the distance from the ground it is, and also in what degrees we are turning, so that when we set up a study with the researchers, they'll go to a location and we can replicate that location exactly time and time again.
Mark found his dream job when he was hired to operate the research crane, which is just a few miles from his home. For this longtime crane operator, there were aspects of the job that took some getting used to.
Everything we do around a construction tower crane is to avoid picking people in a basket. If we're having to pick personnel in a man basket, we would call that meat on a hook. And that just lets you know that that's a very important pick. Over 20 years of operating cranes, I maybe picked a handful of guys in baskets, and here I've probably picked many, many, many thousands of people, so it's just opposite ends.
Even as they probe these 220-foot giants for clues to how our planet functions, these scientists also find time to enjoy the view.
It just gives you an interesting perspective on the canopy, to actually be able to look down on it and see the symmetry of the trees. It's always refreshing. No matter how many times you go up, it's always refreshing to see that.
Another 220 nautical miles up, there's an even more spectacular view from the crane that works on the International Space Station. Launched within the Space Shuttle in April of 2001, Canadarm2 accomplished its first mission flawlessly with the help of its sister crane, Canadarm1, which rides on the Space Shuttle. It deployed itself.
Once the astronauts had unfolded the arm, it stepped off itself from its launch pallet and attached itself to the side of the space station, and then it let go of the, if you like, the launch pallet, and then it became an automatic arm, a robotic arm on the side of the station, which could move around.
Manufactured by McDonnell Detweiler and Associates in Canada at a cost of nearly $900 million, this vital component of the space station is literally allowing us to reach out even further into space with its 54-foot long, 4,000-pound arm.
It is like a video game, but a very complicated one,
We're moving in 3 dimensions. The astronauts have to maintain spatial awareness of exactly where the element is that's being maneuvered towards the station.
Part of the Canadarm2's task is to construct the growing space station. It has already helped assemble the United States airlock, and it continues to add important truss sections to the overall structure, which is scheduled for completion in 2006. The crane also makes occasional use of a special dexterous attachment at the end of the arm, called a human being.
The crews sit on a special fixture on the end of the arm, and they ride on that to various locations where they can perform their tasks. And of course, not only do we transport them there, the platform that's attached to the arm allows the crew, it gives them a work site.
Despite the lack of gravity in space, the cranes cannot be made spectacularly long. Though engineers were able to ignore the static down force of weight in the arm, they had to consider its mass. A massive crane swinging around outside the space station could do a lot of damage. Further, the fine motor skills required of this dexterous crane would be more difficult to achieve if the arm was extremely long. Factors like internal flex and even vibration from the controls are exaggerated the longer the arm.
The Canadarm2 had to have a full operational life of 15 years or greater while being in space in all times. It's not like the Canadarm1, which is part of the shuttle and comes back to Earth with every flight and can be repaired and be refurbished and be maintained. Canadarm2 is going to remain there for the life of the station and the life of the program.
A special feature of the Canadarm2 is that both ends are the same, and each can attach to a power data grapple fixture, or PDGF, on the side of the station. The PDGF links the crane to power, video, and computer data. The crane moves like an inchworm to each PDGF along the side of the station. The next technological step for engineers will be to run the crane entirely from Earth, where operations can be initiated at lower cost and greater margin for safety. But that poses problems.
There's all sorts of challenges with delays, telemetry. You have a very great safety concern, of course, because you do have astronauts and a very valuable asset on orbit. And so we have to make sure that whatever we do is extremely safe, extremely reliable.
The Canadarm2 is an experiment of sorts, a test to see if practical remote operation is feasible. After that, it's on to colonization with our trusty cranes.
The challenges that we have met and overcome with the Canadarm2 will set a very good foundation for building robotic arms for colonization or for activities on planets.
It's tantalizing to think what challenges engineers will face on other planets once our remote-operated cranes have built the rudimentary structures we'll require in order to safely establish colonies. And once we get there, we'll certainly need even more cranes. They'll be cousins to the ones we'll continue to use here on Earth. And they'll be just as indispensable, always ready to give us the lift we need, no matter what planet we happen to inhabit.